So for the final specific outcome in our third and final unit, we're going to look at, well, something that some of you could have predicted. If the unit is about permutations, combinations, and the binomial theorem, and we have covered 3 out of 4 parts without mentioning the binomial theorem, well, you probably figured out that, yeah, the binomial theorem is what's coming up now. So our next goal is to expand the powers of a binomial in a variety of ways, including using the binomial theorem restricted to exponents that are natural numbers. So you might be asking yourselves, what is this binomial theorem thing? What does it mean? Well, we know what a binomial is. It's a polynomial with 2 terms. It talks about restricting exponents to natural numbers. So let's say it's n, and we want to expand powers of the binomial in a variety of ways. Well, we're already used to just multiplying them out. But the binomial theorem uses the binomial term. It's n over r. It's like a fraction in brackets, but without the vinculum, that little line that goes between the numerator and the denominator. Well, this binomial term could actually be expressed as a combination. The reason it's not is because this notation was developed in one context, before this notation was developed in another context, and also before people made the connection that there were 2 different ways to look at the same thing. So why is this relevant? Well, it's because when you're doing your expansion, this x plus y all to the n is going to be x to the n times this first binomial term plus the second binomial term, and x to the n minus 2, y squared, and so on and so forth until we actually end up, if you want we can do this n0, that's going to be 1. We end up with nn, x to the 0, y to the n. So this is actually going to be a tremendous shortcut. I can give you x plus y to the 52 and ask you to expand it. You are not going to want to take x plus y times x plus y times x plus y 52 times and multiply all those out and collect your like terms. That would be very, very daunting. I mean, we are not just looking at millions of terms, not just billions of terms. We are looking at trillions of terms in this particular binomial expansion. That's if you save all collecting of like terms until the very, very end. Nobody wants to do that. But with this expression, we can't jump to any term in the sequence. And that's usually what's expected. There are pretty much guaranteed to be questions like this on your diploma, but they're unlikely to say, take x plus y exponent 52 and expand the whole thing. But they are very likely to say, well, if you have 2x plus 1 over x squared to the 37, what is the coefficient of the term with exponent x to the 0? And then you'll have to take a look at how these exponents work out. So if your first term is x, so you're going to have 2x to the r times 1 over x to the r, or to the n. Sorry, this one will be r, this will be n minus r. And when do you have x to the 0? So when is the n minus r from the first term equal to the negative 2r from the second term? Sorry, that's 1 over x squared. I should make that scribble more legible. Well, that works when we have... Okay, obviously my manufactured example just blew up in my face, but I think you understand the concept of what we're going for. You'll have to do this, figure out exactly which term it is, and jump to that term in the sequence. Might be the 12th term, might be the 20th term, might be the 17th term. But the binomial theorem will allow you to jump to any one term anywhere in that pattern. And they talk about doing it a variety of ways. That's because there's multiple ways to get to it. You can use the combinatorics, or you can use what's called Pascal's triangle. So start with a 1, or if you want, you could think of that as a 1 surrounded by an infinite line of zeros in each direction. And then you add diagonals to fill in the subsequent rows. And this pattern you see here is going to be exactly the pattern that you see in your coefficients in a binomial expansion. So this is called Pascal's triangle, and each row represents part of the binomial theorem and how to get there. You just have to remember that this row that just has the 1 in it, that is the n equals 0 row. And the 1 and 1 is n equals 1. This is n equals 2. So the n number for the row is 1 less than the number of elements in that row. So if you have 4c2, well, you find row that's 0, 1, 2, 3, 4. C2 means our R is 2, so that our R values go 0, 1, 2. Boom, 6. So if you take 4 factorial over 2 factorial, 2 factorial, you get 4 times 3 times 2 times 1 over 2 times 2. So your denominator is 4. That cancels with this. And we're left with 2 times 3, or 6, within our Pascal's triangle. So we will have multiple ways to get to the final result. In this case, the most efficient is to do that NCR equivalence, especially since that is now a common feature of modern calculators.